So hopefully that's better. Yeah. Anyway, so non-linear equations are equations that are not linear. If it's linear, you know how to solve it. If it's one dimension, you just divide by the number. It's trivial. If it's in several dimensions, you put it in matrix form, it'll be AX equals B, and you can solve it using the methods we've done so far. If it's non-linear, then we will use methods from this. So there's two types of problems that are basically the we'll look at this week. So it's finding the roots of a set of equations in general, or a single equation if we're in one dimension. So if you want fx equals c, or fx minus c equals 0, so we want to find the zeros. So if it's a linear equation, it'll just be a single solution there. But if it's a polynomial in general, you know, there may be two solutions, etc. That's finding the roots of an equation, so finding the values where a function is equal to 0. If instead we want to find where a function takes its maximum or minimum values, so I don't know, in economics, I think Martin puts up some of those problems in the first year. You know, there's some function you want to optimize, or machine learning, you want to recognize the most handwriting digits or something like that. What you want to do is to optimize some function. And going back to calculus, if we want to optimize a function, we find the extreme of the function by finding where its derivatives are equal to 0. And that, of course, is exactly the same problem as the root finding, but instead of finding the roots of fx, we're looking for the roots of the derivative of the function. So it's basically the same thing. So how do we find these roots of the equation? Well, the well-known algorithms, ones that we'll sort of talk about mainly here, are these ones: bisection, Newton-Raphson, and secant. I imagine you've kind of seen those before. We'll go through them in a second, but they're all based around, a bit like last week, basically making a Taylor expansion of your function. So you say it's equal to the value at some point, the one where you start, plus some amount of the derivative, plus some amount of the second derivative. And then you say that that's going to be equal to 0 once you've moved the appropriate distance, and off you go. All of these methods are based around that. Take the Taylor expansion, write down under what conditions, if that expansion holds, the function will be equal to 0, rearrange to get the how much you must move, and then do that. I should say the exception is it my computer making funny noises, or is it someone's mic on Teams? Not sure. Bisection's the sort of slight outlier. It's kind of a geometric argument. So if f is continuous, if it's a continuous function, you find somewhere where it's positive, somewhere where it's negative, and for a continuous function, it must have crossed through 0 between those 2 points. So what you do is you cut your interval in half, and you see which half of the interval that you've cut it into still has a negative and a positive sign, and then you know that it must be in that new halved interval, that bisected interval, that the new point must be. That the root must be. And you just rinse and repeat This is kind of slow. Each time you bisect, you reduce your possible error. You know what range the root is in. You reduce it by half. So you're halving your error on your root each time. If you've got a function that's got multiple roots, then you'd need different starting conditions to find the different roots. That goes in general. I should turn off the lights as well at the front. It's pretty hard to see that projector. Okay, Newton's method, Newton-Raphson kind of method. So what you've got is your function y. It's just fx at some position. You know the value of this function and its derivative at the point xn. So x0 is your first point. So you've put your measuring device, or just typed into the computer what your starting x value is, how far along the graph you are, and you compute the value of the function fx at that point, and you calculate the derivative at that point. Or if you're programming, you perhaps have a function that calculates the function at that point, a function that calculates the derivative at that point. And then you say my estimate at the point y, which is at the value of the function at the point x, that's going to be equal to the value of the function at the point you're at plus the derivative at the point you're at times the point you're at minus however far you go. And so x is what you're trying to find. And what we want is that y, the value at this new point that we're trying to work out how far to shift along, we want that to be equal to 0. So we want the left-hand side to be equal to 0, and we'll call this new point x xn plus 1. So we're going to do it iteratively. We will find the next point, and then we will keep repeating. The reason this isn't is because this is a first order Taylor expansion. As I said, you're assuming that only the first derivative term is important, and you've just chucked away everything to do with the second derivative, third derivative, and so on. So this equation is only an approximation. So this equation is only an approximation, and you won't immediately end up with at the root. But as you get closer and closer to the root, any sensibly behaved function will start to behave more and more sensibly, and you'll close in. So if I set the predicted point value using our simple model function equal to 0, if I rearrange for the new point, so to find out how far along, how much of the gradient term I should be adding, I get that it's equal to the old data point minus the ratio of the value of the function divided by its gradient at the original point. Obviously, this means that you need your derivative to be well defined. If you've got a function that's got derivatives that go to 0 at some values, or you've got discontinuities and stuff, things will be tricky. And there's a stolen animation from Wikipedia from some, I'm guessing it's German-ish site, maybe it's Dutch, I don't know, should I ask Bart, that sort of shows how it works. But basically at each point you draw the tangent, where's the tangent cross the 0, move to that point. If your function was linear, job would be done. Because it's not linear, that's only an approximation, and you've still got something to do. I'd suggest just to sort of get a bit of practice in, you have a go at just coding up some simple-ish examples. Find that Newton method to solve those different equations. If you get pen and paper out or plot them or whatever, you should see how many solutions you're expecting. And by varying where you start in the bisection or Newton algorithm, you can probably find the different roots of the equations. Right. Does that all look sort of familiar-ish? So the task there in the first bit is just to, so I know some of you will go back and try and find the previous notes and when you did it before, but I think it's quite useful maybe even just to sit down and try and code it up, practice what you've been doing this week, but up to you. Okay. Now, Newton's method is nice, but sometimes calculating the derivative is a bit of a pig. Perhaps like me, you're not very good at differentiating complicated functions. You forget most of those things. So instead of going through pen and paper and doing the derivative, what we could do is we could take an approximation, a finite difference approximation to the derivative at the point we want. So if we've written our bit of code that calculates the function we want at a given point, we can make two calls to that function. We can calculate f at the point we want plus delta x, where delta x is small. Take away fx and then subtract the amount we've shifted. So we just make a numerical, simple finite difference approximation to the derivative, and then we plug it in exactly as before. So these equations, they look a bit fiddly, but they're only just plugging in what this equation is. So you just make a numerical approximation to the derivative to save you either having to work out what the derivative is. That's hopefully you can do that actually, but sometimes it's computationally more expensive to calculate than the function itself. So it can be efficient to just calculate the derivative twice. It's also another very good test. If later on, if you're calculating derivatives analytically, you've worked out the value of the thing, it's a good idea to check that they give you the right values by doing a numerical finite difference calculation of the function and see if the derivative from your fancy function is the same as the one you get from the brute force finite differences. And for that same reason, once you've done the Newton method, I think it'd be quite a good thing to code up the secant method, check your derivatives match, check that you get basically the same solutions. It's a non-linear problem, you'll get slight differences, but you should end up in basically the same point. I'll try and speed up a bit. Optimization is basically the same thing. This time we'll write out a quadratic, so a Taylor expansion with an extra term will include the second derivative of the function. So we've got on the left-hand side an estimate of the function at the new position. The new position will be k plus 1 at the x at k plus 1. At the moment we're at xk, and so our estimate for what the value of the function will change to will be the value of the function where we are, at where we are times however far we move. That's what we had before, and then we're going to add in the second order term. That's the second derivative and the square of the distance that we move. And what we're going to want to do in this case is to set the derivative of the function equal to 0. We can do that in various ways. I suggest you have a little play around with that equation. If you try and figure it out for yourselves, what you should find is it looks exactly like the Newton, like the root finding one, but instead of the function divided by the derivative, it's the derivative divided by the second derivative. So have a look, you'll be plenty of examples online. It's the same thing, set things equal to 0, rearrange for the k+1 term, and it will pop out. And C, I think these are the examples I'm not sure I've put up on the thing, but see if you can find the solutions, the minima of those functions. Again, have a think about how many minima you might expect for the different polynomials. And the last thing to mention is essentially this stuff goes over easily to multiple dimensions. So you've got multiple independent variables. So if our function is something that maps a vector, so if you've got k x values, so it's x0 along the first axis, x1 along the second, you plug in that set of x values and it gives you back a number. Then we have that result. No, so it's a so if you've got a vector function, so it's a the function it returns it is on a vector, so it's got values f0, f1, da 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 da. So you give it a set of x coordinates and you get sort of a set of f values back. The equivalent of the first order Newton root finding equation looks like this: that the new values of your function are going to be the values of the function at working point plus this thing here, which is called the Jacobian of the function times the distance you've moved. And so the first line of this is how much the first component of the f vector varies as you change the first independent variable. Then it's how much that first component of the variable changes as you change the second variable. And that's multiplied in each case by the distance you move along each of those different directions. So this is just a matrix form of that vector equation. And what you're going to want to do is to set each of these, each component of the f vector equal to 0. So this thing here should be equal to the null vector. And this is just a set of equations ax equals b. So instead of with the Newton method in one dimension, just saying that the new point is the old point minus function divided by the old function, this is the equivalent of it. And if we were sort of to cast it in the same language, we would be calculating the inverse of this derivative matrix and using that, multiplying that by the old points to get the new things. So we're solving for delta x in this case. So the delta x is how far we move along each of the independent directions. And the optimization works exactly the same. If we've got a scalar function, so if f and you feed it in a set of x coordinates, so x0, x1, da da da, how far along the different directions you go, and it returns you a number, and you want to find which position of those x values will give you a maximum value for this function. Then what you want to do is to minimize the gradient function, the grad of this function. So the grad of the function is the derivative of the function with respect to each of the coordinates. So it's the function divided by differentiated, taking the partial derivative with respect to x0, and then the next component is f divide partial derivative with respect to x1, x2, and so on. And so you want each of those components to be equal to 0. That's the equivalent of the derivative being 0 in one dimension case. So the function, first derivative of the function, partial derivative with respect to each coordinate will be 0. And you can write this out. It kind of looks like that. So what we do, so once we take the gradient of our function, so we've got df by dx0, so that's the first component of the grad of the function, and we want that to be equal to 0. So what we then have is now a vector valued function, so it's the grad is has got one component along each of the directions, so it's basically the root finding problem again. So we've got, in this case, instead, a matrix of second derivatives. So the first derivative gives us this grad vector, and that converts the problem into the problem that we had of finding the roots. So we're finding the roots of the gradient function. And again, that's AX equals B. So you set up your matrix and then you solve it. And again, because it's going to be a non-linear problem in general, you won't get exactly the solution. But what you do is you iterate. You set up this matrix of derivatives, solve the linearized problem, and then rinse and repeat. That's it. There's a lot of complications for doing these problems reliably in the real world. We're only going to sort of touch on them, but if you're sort of fairly secure on those basics, everything else sort of follows from that. So on the blackboard, there's also a little 2D example. It might be, I'd suggest for the second, the multi-dimensional example on Blackboard, it might be easier just to do it pen and paper rather than coding it up, or certainly do it first. Just try and check that you're okay where the terms are. And I do suggest that you go through and try and check the derivations of where these things are coming from. They're always just Taylor expansion, set it equal to 0, rearrange, calculate the appropriate numbers of functions, derivatives of functions, solve the equation and repeat. Basically the same stuff repeatedly. Right, that's the talking at you bit done. Are there any questions?